All right, welcome back. We've moved on to Unit 9 now. We're going to be talking about bonding for the next couple of weeks. Bonding, a lot of it should be review, stuff you've learned about both in earlier chemistry classes and some things that we've actually covered in this chemistry class will come back up. Like, for example, you already know the types of bonds, but you don't necessarily know why they occur, which is one of the things we're going to be talking about today, and then we're also going to be talking about how to actually illustrate what a bond looks like, okay? So what is chemical bonding? How would you define it? Okay, bonding is the combination of two or more atoms to create a molecule of more stability. In other words, atoms that are missing maybe electrons in their outer shell that they want to have filled up will bond with other electrons, share those electrons, or steal those electrons in order to make that shell full and thus more stable. Okay. So atoms bond in three possible ways. They can share electrons equally, they can share electrons unequally, or the electrons can be donated from one atom to another, okay? And the type of bond and the way that they share or donate their atoms, or as we like to say, steal their atoms, okay, is based on electronegativity. Now that word probably rings a few bells from the last unit that we did, and you know now that the trend for electronegativity is that it increases as you go up the periodic table, and it increases as you go to the right on the periodic table. So how does that electronegativity actually affect bonding? Like, what does it mean? Like, what does it have to do with anything? Well, what you need to do is you calculate the differences between electronegativity of your two atoms that are about to form a bond or form a molecule. Okay, for example, Na and Cl. Now, I don't expect you to know these numbers off the top of your head. You can actually find them on the periodic table. If you're using the Sergeant Welch one that we do, on the back of that color version that I gave you, there are boxes, and each element has its own box, and there's a list of different numbers in there. One of them is electronegativity. Again, if you're using the Sergeant Welch one, it's the top right number in the box. Usually it's written in black. It's also found if you're using an iPad app like the K12 app. That's a good one. If you click on the box of each element, it's actually listed at the top under electronegativity, or ENV, I believe it says. Okay? So, anywho. For Cl, the electronegativity is 3.16. Again, I don't expect you to know that off the top of your head. Find it on the periodic table. For Na, it's 0.93. Now, when I subtract those two, I get a difference in electronegativity, or a delta En, delta obviously meaning change or difference, and En meaning electronegativity, of 2.23. So that is the difference of electronegativity between the two. Okay. Another example might be NCl3. Okay. Again, Cl is 3.16, N is 3.04. Now, you might ask, well, how do I know which one to put on top? It doesn't matter as long as the larger number is on top. We don't ever have negative numbers here. So if 3.16 is, or Cl isn't necessarily always on top, it's just whichever one's bigger. So 3.16 minus 3.04 gives me a difference in electronegativity of 0.12. Now it's important, since this is NCl3, to note that the subscript does not matter, because all we're really doing is comparing the pull of one Cl to one N, because when you have multiple atoms that are bonding, okay, they aren't pulling all together. They're each pulling individually on the element that they might be bonding with. Okay, so let's talk about the three types of bonds. Okay, the first one you know well. Okay, it's covalent bonds. You should have learned about that in biology, and we talked about it in the first semester. That's when a bond, that's a bond where electrons are shared pretty much equally between the two. So when you calculate that electronegativity between these two atoms that are in a covalent bond, the difference in electronegativity will be less than 0.2. So anytime you do that calculation and it's less than 0.2, it's a covalent bond. A good example would be that NCl3 that we just did. It had a difference in electronegativity of 0.12. Okay, Cl2 is another example. Okay, now you may say, well, where's the other atom? Well, it's just Cl bonding with itself, so it's Cl minus Cl, 3.16 minus 3.16, which gives me a difference of an electronegativity of 0. Now that's important because that is completely equal sharing. Okay, the closer number that we are to 0, the more equal the sharing. So as we get away from that 0.2, when we go beyond 0.2, then we get into what's called polar covalent bond. And that's when the electrons are shared unequally. They're actually going to be pulled more towards one side than the other side. An example, a really good example, is H2O. You probably did some drawings of H2O when you were in biology class and maybe looked like Mickey Mouse, where O is the large atom on the bottom, and then there's two smaller H's perched on the top of it. Now, the reason they're perched on the top is because of the change in electronegativity. The difference is 1.24, which means that this oxygen has a stronger pull on the electrons of hydrogen than hydrogen does on the electrons of oxygen, meaning that the oxygen side will be more negative and where the hydrogens are will be more positive. Okay? Another example is F2O. Its difference is 0.55. Again, not as strong a pull, but still polar. Okay? So BCl3, take a moment, see if you can figure it out. Okay, well, BCl3, that's going to be, that is polar. Okay. The last bond is ionic bonds. That's when electrons are actually stolen from one and placed in another. Usually they're stolen from a metal, or the metal gives up its electron, or 2 electrons, or 3, whatever it may be, and then gives those up to a non-metal, making the non-metal a negative anion and the metal a positive cation. And then it's the actual attraction of that positive to negative which causes the bond to occur. Okay? This is found anytime the change in electronegativity is greater or equal to 1.7. A really good example is salt, sodium chloride, NaCl, 3.16 minus 0.93 gives me a difference of 2.23. Okay, so now you know why the bonds form and how to calculate which bond will form if you had two if you had two atoms and you weren't quite sure what type of bond they would form. Just use electronegativity. Okay. All right, let's talk about valence electrons and what they have to do with bonding. Okay, valence electrons are the electrons found on the outermost shell, and they are the only ones that are capable of bonding with one another or with another atom. Okay, you can determine the valence, how many valence electrons an atom has, just by looking at its group number. Okay, and we're going to focus on the A groups, meaning we're going to leave out the transition metals. Okay, so group 1A, for example, is just the group with Li in it. Those all have 1 valence electron. 2A all has 2. And then we skip the transitions and go to 3A, which was where B is. That one has 3, and then so on and so forth until you get to the noble gases, which have 8 valence electrons. Okay. Now we can represent those valence electrons on something called the Lewis dot diagram. Okay. That's when you take those valence electrons, those different amounts of electrons, and you place them around the chemical symbol. Okay, Li is in the first group, it has 1 valence electron. Be has 2. Now you'll notice instead of pairing them together, I put them on opposite sides, and that's important because as soon as a pair is formed, no bond can occur on that side. For example, look at oxygen. Okay, oxygen cannot form bonds on this side or on this side, but it has 2 open spaces, so it can form 2 bonds. Okay, Be can also form 2 bonds. Okay, but it's not going to have a full outer shell. Okay, you could tell the only ones that are going to have a full outer shell are things from C on, because C obviously would bond with 4 other electrons to fill its outer shell. Okay, and that has something to do with what we call the Octet Rule. Okay, this table is very important. This just lists the groups. The atom at the top of that group, we're going to leave hydrogen and helium out of this talk just because they have special rules and get a little weird. This is the list of valence electrons for each group. Obviously, it matches the number, 2A2. This is the number of bonds that each one can make. And again, that's based on the pairs. So you'll see here, C can have 4, okay, which means if it paired 4 times, it would have a completely full outer shell. So it is part of the Octet Rule, which means that when these guys start bonding, everything from group 4 on, then they have to fill up their outer shell. And that'll be important for when we go to actually show the bonds when we do our drawings here in a little bit. Okay, B, group 3, does not apply to the Octet Rule because if it forms its 3 bonds, it'll have 2 open spaces, okay, and only has 6 total electrons. Okay, so this Octet Rule, okay, applies to group 4A and on, okay, and it means that you have to completely fill the outer shell when bonding. Okay, so this is what that might look like if we were going to bond hydrogen with those different elements. Okay. So let's talk about how we're going to draw these, how I'm actually going to be checking to see if you kind of know what you're doing. This is going to be our first assignment here. Okay. For ionic bonds, there's 3 steps, okay, and the first 2 actually are kind of combined. First, you're going to draw the atom's dot structure. So for NaCl, Na has 1 valence electron, it's in the first group. Cl has 7 because it's in the second group. Now you'll notice my 1 dot for Na corresponds to an open space here for Cl. Now, are they going to be sharing that electron? Well, not if it's ionic. Remember, if it's ionic, that electron is going to actually be transferred. So that's step 2. Okay, you're actually going to draw an arrow, okay, from your 1 single electron on Na to the open space on Cl where it will go. Okay, and then below that, on step 3, you're going to show the final form. Okay, so take a guess. How many valence electrons will Na have? Yeah, that's right, 0 because it lost its 1. how many will Cl have? Well, now it had 7, it added 1, so it has a total of 8. So once I've done that, then I just add the charges, and I'm done. Na plus 1, and then Cl minus 1 with its 8 valence electrons. Okay? So that's how I would expect you to draw an ionic bond. Okay? Now, covalent bonds are easier to draw, I think, but they include more steps. Okay? So let's take a moment here to run through these. Okay? Step 1, we need to determine the total number of valence electrons. So let's say that I was going to work with carbon tetrachloride. Okay? Well, carbon tetrachloride has 1 carbon atom, okay, and each carbon atom has 4 valence electrons. 1 times 4 gives me 4 valence electrons total. Chlorine, okay, has 4, there's 4 of them because it's carbon tetrachloride, I have 4 of them. So 4 times its total number of valence electrons, which is 7, gives me a total of 28 valence electrons for Cl. When I add those two totals together, I get a total number of 32 valence electrons for the whole thing. So when I'm done drawing this, I should have 32 dots. Now, quick note, if it happened to have a charge, if it was a positive charge or a cation, I would actually subtract from this number. If it was an anion that had a negative charge, I would add to that number at the end. Okay, quick little note because that's going to come up on your assignment. Okay. So number 2. Place the least electronegative element in the center. Now, you can look up those numbers that we talked about earlier, or just look at the periodic table. Okay? Cl is all the way on the right side next to the noble gases. C is about 3 or 4 spots away and up 1. So which one's going to be the least electronegative based on that? Well, it would be C. So I'm going to place C in the center, and then I'm going to place all the remaining atoms, which is the 4 chlorines, around it. 1 above, 1 below, 1 to the right, and 1 to the left. So that's what that would look like. That's step 2. Now step 3, okay, I'm going to check the octet rules and I'm going to form bonds. Okay, since I need 4 bonds here because there's 4 chlorines going around that C, so I'm going to have 4 lines in between. But since Cl is in group 7, okay, the octet rule applies. So once I've drawn it, I need to draw all the electrons around the outside of the Cl. Now, the octet rule would tell you obviously that I should put 8, okay, but since C and Cl's are sharing these guys on the inside, instead of putting dots there, I'm going to draw actual bonds. Each one of these lines represents a bond, which means it represents 2 electrons. So if I actually counted it, I'd say 1, 2, 3, 4, 5, 6, and then this would be 7, 8. So technically they all have 8 around them, including the inner element, the C, okay? C, the octet rule would also apply to, but since it has these 4 lines around it, those represent the 8 electrons. So therefore, it also has an octet that we talk about right here. So it's already been filled in for us. So now, how do I check to make sure my work is correct? How do I know I've done this right and I don't have to do double bonds or anything like that? All you need to do then is count the number of dots, okay, 6, 12, 18, 24, and bonds. 26, 28, 30, and 32. There, and if I go off that number I had earlier, okay, that would be my 32 electrons. Okay, so again, step 4, count the valence electrons. Each bond counts as 2. That number should match that number that you came up with at the very beginning. Now, what if it doesn't? That takes us to step 5. Okay, let's look at CO2. If you have that handout, if you've downloaded it, or if you have the copy from the class, okay, this would be, I think it's letter K on our assignment. Okay. So, yeah, letter K. I keep saying K today, so I don't know why that is. Anyways, so I've got my 1 carbon. Has 4 valence electrons, so that's 4 VE minus there. Okay. I have my 2 oxygens, so 2 times its 6 valence electrons gives me a total of 12. When I add them together, I get 16. So when I draw this, I should have 16 valence electrons. Okay, that was step 1. Step 2, put carbon in the center and then put the O's on the outside of it. Okay, step 3, now I start adding my bonds, and then I find the octets, okay? O, the octet rule applies to. It's in group 6, so I need to put all of its dots around it. Remember that these bonds here represent 2 dots, so I don't have to put those on the inside there. But even if, let's say this was carbon on the outside, okay? If the octet rule applies, you always fill it in, okay? You can go back and fix it later, and that's what we're going to show here, okay? Carbon, the octet rule applies to, so I have its 2 here on either side, but I also need 2 above and below, okay? If it was something like maybe B and the octet rule didn't apply, then I wouldn't have to draw the extra dots around it. Okay? So let's count these up. My total number of dots, 2, 4, 6, 12, 14, 16, 18, 20. Okay, we got problems right here in River City, okay? Step 5, Rule 5. If your structure has too many electrons compared to your expected count, you need to circle pairs of adjacent atoms. So they have to be in pairs and they have to be adjacent, meaning side by side on different atoms, okay? So I have two sets of those. I have one here on the top and I have one here on the bottom. So let's do the one on the bottom, okay? I'm going to circle those 4 and I'm going to replace the 4 dots. I can get rid of them. I'm going to replace them with multiple bonds. So I'm going to put a second bond there in replacement of those 4 electrons. So in other words, those 4 electrons now are being represented by these 2 lines. That's why I took 4 now and only added 1 line. Okay, but now my total is only 18. Well, I need to have 16. Is there any other adjacent pairs that I can get rid of? Yeah, right here on the top. So I'll circle those. We'll get rid of those, and we'll add another bond. Okay, so now I have a total of 2, 4, 6, 8, 10, 12, 14, 16. So that means in carbon dioxide, there are double bonds between the carbon and each one of the oxygens. Okay, so there's a quick rundown of the rules for covalent bonds. You may want to have that up, keep that somewhere safe. That table is very important. Make sure you have that copied. And then this set of rules and then the rules for the ionic bonds drawings are also very important. Okay, hope you learned something. Feel free to rewind, come back, ask questions. Visit mrkubuske.wordpress.com for all your documents and notes. Have a great day. We'll see you next time.